Let's take a look at some of these problems and see if we can do some free body diagrams to help us out. So for number one, let's go ahead and if we were to sketch a free body diagram, I'm going to include friction, but I'll draw it as a dotted line just to kind of indicate that we're going to do this system both with and without friction. So just to be clear, if I were given the force, we'll treat this as a given, and if we wanted to get the acceleration in terms of m, g, and mu, um, that would be our goal if we were given friction in this problem. And also in terms of capital F, our given force. Well, without friction, we have a pretty straightforward situation where the normal force balances the weight, and the applied force just equals ma, so our acceleration is just going to be F over m. Now, when we actually have friction, we're going to need to use this equation, Fn equals the gravity force, which is the same as the weight, so that's mg. And so we can get our friction as mu times the normal force, which is going to give us mu times mg. And so in that case, when we set up our horizontal equation, we actually have F minus the friction equals ma. And that's F minus mu mg equals ma. So it actually turns out that in this case, our acceleration is going to be F minus mu mg all over m. So that's how we get our acceleration in that particular case. So that's fairly straightforward. Things get a little trickier when we want to put things at an angle. So for example, in problem 2, we've got a little bit of a different situation where we've got a normal force. We've got this force F at an angle theta. And so we have friction going backwards, and we have mg, the weight, pointing downwards. You can actually write it like that on the AP. Now let me just do a little color coding here. This will be F cos theta, and pointing upwards will be F sine theta. And so let's set up our equations. Vertically speaking, we've got the normal force trying to work with the sine theta component of our diagonal force. Both of those are balancing mg, which is totally fine. And again, our goal here is we want to get the acceleration of the system in terms of F, theta, mu, m, and g. That's our goal here in this particular problem. And I'm going to actually do this with friction, because without friction, you just set friction equal to 0, and it's a little easier. Now, in the horizontal direction, we're going to end up getting F cosine theta competes with the friction in order to make the mass accelerate. Now, we need to get the normal force in order to get friction, and I can actually use equation 1 right here to do that. So when I do that, I'm going to actually get that the normal force is mg minus F sine theta. And if you notice, I've got my normal force in terms of all known values, things that would be given to me. So now let's get our friction force as mu times normal, which is going to be mu mg minus F sine theta. And so what I want to actually do here is plug that in to solve for my acceleration. So I'm going to end up getting F cosine theta minus mu mg minus F sine theta divided by m gives me my acceleration. So that's actually a really, really good system. I don't know, we do a lot with this on the exam. There's a couple questions, I think. This is actually a system worth studying and knowing fairly well, actually. So actually, there are a couple questions that you should be ready to do with this particular system. Strangely enough, I didn't do a lot with inclined planes. So number 3. Let's actually look at it if there were friction acting on it. I did a little bit with inclined planes, but not a lot. So we're going to have a normal force like this. We're going to have the weight pointing down, and the weight gets split into 2 components. So we've got mg cos theta, remember, cosine cancels contact, and mg sine theta, which makes a slide, but we've got friction going this way. So normal force balances mg cos theta, and the sine component of the weight competes with the friction in order to make the mass accelerate. Now let's go ahead and get friction. So friction is mu times mg cos theta. And let's just remember, our goal here is I want to get the acceleration of the system in terms of mg, theta, and mu. No other letter can be in my acceleration term. So now when I actually solve and substitute, I have mg sine theta minus mu mg cos theta equals m times a. All the m's cancel out, and it actually turns out my acceleration is equal to g sine theta minus mu times the cosine of theta. And that's how we get the acceleration. All right. That's pretty good for those. For number 4, that's another good one to know how to solve. There's actually a practice problem like that on the AP, so I'm going to leave that one alone. Number 5, it's good to know how to do, but I didn't put it on the test. I didn't put number 6 on the test, and I didn't put number 7 on the test. Number 8, I skipped. Number 9, though, might be a little bit useful. Let's take a quick look at it. So number 9, I've got this force F pushing the block into the wall. So here are the forces. I've got mg acting down. The reason it doesn't slide is because there's friction acting up. I've got a force applied this way and a normal force pushing back the other way. We have this coefficient of friction mu with the surface. So let's be clear. Friction balances weight, and our goal is to find the minimum F to hold the block to the wall. So friction equals mg because they balance, and the applied force balances the normal. So let's see what we can do here. I know that friction equals mu times n. And so friction over mu is going to equal the normal force, but I know that friction is mg, so I know that the normal force is mg over mu, and since that balances the applied force, that gives me an applied force of F equals mg over mu. So that's the minimum force necessary needed to hold the block up. Number 10 was a great practice problem, as were 11 and 12, but we're not going to worry about those on this exam, so I would just restrict your attention to the problems that we've done here. Hope that was a little bit helpful.